Hello children, welcome back to Physics with Sanob. In this video, we will be discussing the previous questions from the chapter Thermal Properties of Matter. See, we will be discussing all the previous questions of NEET and before that AIPMT. Okay, let's go to the first question. That is a copper rod of 88 centimeter and aluminium rod of unknown length have their increase in length independent of increase in temperature. See, increase in length delta L is original length coefficient of linear expansion and the rise in temperature. Okay, so this is for copper rod and this is for aluminium rod. The length of the aluminium rod is unknown, that we have to determine, right? So L2, this is the increase in length of copper and this is the increase in length of aluminium, and they are equal independent of the temperature. Means whatever be the rise in temperature, these two will be equal. Okay. So we can write L2 equal to alpha 1 L1. Alpha 1 is the coefficient of linear expansion of copper and it is given as 1.7 into 10 raised minus 5. That of aluminium is 2.2 into 10 raised minus 5. Okay, and the length of the aluminium rod is 88 centimeter. Okay, this 10 raised to minus 5 and 10 raised minus 5 can be cancelled. Then 2.2 divided by 88, that will be 40. So 17 into 4. Okay, this is 40 into 1.7 means 17 into 4 and it will be 68 centimeter. Right. Okay, now let's see what we have next. Coefficient of linear expansion of brass and steel rods are alpha 1 and alpha 2. Length of brass and steel rods are L1 and L2 respectively. If L2 minus L1 is maintained same at all temperatures, which one of the following relations holds good? Okay, original length of the steel rod is L1, and when it is heated through delta T, its length will become L1 dash. Okay, so L1 dash will be L1 times 1 plus alpha 1 delta T. Okay, and for brass, original length is L2. When its temperature is increased by delta T, length becomes L2 dash. So L2 times 1 plus alpha 2 delta T. Okay, so the difference in length after both the rods are heated through the same temperature. So L2 dash minus L1 dash, it is same as the difference in their original length, means L2 minus L1. See, L2 dash minus L1 dash is equal to L2 minus L1. Means this term must be 0. Okay, so we can equate this to 0. So we will get alpha 1 L1 equals alpha 2 L2. Okay. Next, the value of coefficient of volume expansion of glycerin is 5 into 10 raised minus 4 per Kelvin. The fractional change in the density of glycerin for a rise of 40 degrees Celsius in temperature. Okay, now see rho, that is the density, that is equal to mass over volume. And when it is heated through delta T, mass will remain unchanged. Okay, so rho dash will be m divided by new volume will be original volume times 1 plus gamma delta T, where gamma is the coefficient of cubical expansion. Okay, now this m by v, right? See this one, this m by v, that is the original density rho. Okay, so rho divided by 1 plus gamma delta T. Okay, now when this 1 plus gamma delta T is taken to the numerator, it will be 1 plus gamma delta T raised to minus 1. Okay, 1 plus gamma delta T raised to minus 1, and it can be written as 1 plus gamma delta T raised to minus 1 can be written as, see, this is actually rho times 1 plus gamma delta T raised to minus 1. Okay. See, using binomial theorem, see how do you write this 1 plus x whole raised to n? This will be 1 plus nx. The next term will be n into n minus 1 x square by 2 factorial, like that. Okay, now see what stands for x here. See, it is gamma delta T. See, gamma, it is given 5 into 10 raised to minus 4. It is very small compared to 1, this gamma. And delta T, the rise in temperature is only 40 degrees Celsius. Okay, so this term gamma delta T is much smaller compared to 1. Okay, so the terms containing higher powers of it can be neglected. Okay, so we can write it is nearly equal to 1 plus nx. What stands for n? That is minus 1. And what stands for x? It is gamma delta t. So it can be written as 1 plus minus 1 into gamma delta t, or it is 1 minus gamma delta t. Okay, now see, this can be written as rho dash by rho minus 1, that is minus gamma delta t. So rho dash, final density minus original density, that is the change in density, divided by original density, that is the fractional change in density. Okay, now that fractional change in density that we have to determine, right? Yeah, it will be minus 5 into 10 raised to minus 4, that is gamma delta t is 40. See, 5 into 40, that is 200 into 10 raised minus 4, that is 0.02, right? 0.02. And what is the significance of this negative sign? Means there will be a decrease in density. Okay, so negative sign is only to show that density decreases. So this must be the correct option. Okay, now let's see what we have next. On a new scale of temperature, see, we have this Celsius scale, Kelvin scale, Fahrenheit scale. See, for Celsius scale, for any temperature scale, there will be two fixed points. Ice point, or it is called the lower fixed points, and steam point, or it is called the upper fixed points. Okay, now suppose we have a water bath and its temperature on Celsius scale is, say, C. In Kelvin scale it is K, and in Fahrenheit scale the same temperature is, say, F. So this F degree Fahrenheit, C degree Celsius, and K Kelvin are the same temperature. Okay, see, for any temperature scale reading, okay, reading minus lower fixed point of that particular scale divided by upper fixed point minus lower fixed point, this will be constant for any scale. Here we have got two scales. One is Celsius scale and the other is an arbitrary scale, and it is being called as W scale. Okay, W scale. Now for the Celsius scale, suppose the reading is C, and on the arbitrary scale, suppose the reading is W. Let's call it W scale. And the lower fixed point, that is usually the melting point of ice, on Celsius scale it is 0 degrees Celsius, and on this arbitrary scale it is 39, and it is given as 39 here. Okay, and the boiling point of water, or the upper fixed point, for the arbitrary scale it is 239, and for Celsius scale it is 100. If you take this ratio for any scale, it must be the same. We have that ratio for Celsius and the same ratio for the arbitrary scale. Okay, so we will get C by 100, that is equal to W minus 39 divided by 239 minus 39 will be 200. Okay, so we will get 2C, that is equal to W minus 39, and W will be equal to 2C plus 39. See, actual Celsius reading is 39 degrees Celsius. What would be the reading on the arbitrary scale? Okay, means what would be this W scale reading? Okay, it will be 117. Okay, this one, right? Now two rods, one made of copper and the other made of steel, of the same length and same cross-sectional area, are joined together. Thermal conductivity of copper and steel are 385 okay, SI units and 50 SI units. Okay, the free ends of copper and steel are held at 100 degree and 0 degree. The temperature of the junction is, suppose the junction temperature is T degrees Celsius. These two rods are connected in series, so the rate of flow of heat through both the rods will be the same. See, when two resistors are connected in series, electric current will be the same through both the resistors. Similarly, when two conductors are connected like this, rate of flow of heat through both the conductors will be the same. Okay, now see, how do you find the rate of flow of heat? It is Ka T1 minus T2 by L. Okay, so for the first copper rod, K1A by L. And see, this is the copper rod. Temperature at one end is 100 and at the other end it is T. Okay, so it will be 100 minus T. This is the rate of flow of heat through the copper, and this is the rate of flow of heat through the steel. It is K2A by L into T minus, see, at one end of the steel rod the temperature is T and the other end it is 0. Okay, now children, here we have this A by L, here also A by L, that can be cancelled. And when this K1 is taken to the right, on the right side we will have K2 by K1. Okay, see K2 is 50 and K1 is 385. So 50 by 385. Okay, now here we have T here. When it is taken to the left, it comes in the denominator. So 100 by T minus T by T is 1. Okay, 100 by T minus 1. You can take this minus 1 on to the right side. So it will be 50 by 385 plus 1. Okay, so it will be 435 by 385. And T we will get, this is 385 by 435 into 100 and it is 88.5 degree Celsius. Okay. Now the power radiated by a black body is P and it radiates maximum energy at a wavelength lambda 0. Okay, it's Wien's displacement law. Okay. Now see, if the temperature of black body is now changed so that it radiates maximum energy at wavelength 3 by 4 lambda 0, the power radiated by it becomes Np. Okay, the value of N is. Now see, lambda proportional to 1 by T by Wien's law, lambda T that is equal to constant, so 3 by 4 lambda 0. This lambda T constant means lambda 1 T1, we can write lambda 2 T2. Okay, so 3 by 4 lambda 0. Okay, when the wavelength corresponding to maximum energy radiation is 3 by 4 lambda 0, suppose the temperature is T dash. Okay, when the wavelength corresponding to maximum energy radiation is lambda 0, temperature is T. Okay, so we will get T dash by T equal to 4 by 3. Now the power that is proportional to T raised to 4. So P dash by P that is equal to T dash by T whole raised to 4 and it is equal to 4 by 3 raised to 4. 4 raised to 4 that is 256. 4 raised to 4 means 4 square into 4 square means 16 into 16, 256. And 3 raised to 4 is 3 square into 3 square, 9 into 9 that is 81. Okay, this must be the correct option. Okay, now let's see what we have next. Two rods say A and B of different materials are welded together as shown. Their thermal conductivities are K1 and K2. Thermal conductivity of the composite rod. Here the two rods are attached or connected or welded together in parallel. Okay, see, when two conductors are connected in parallel, see, 1 by R, just like in electricity, 1 by R equals 1 by R1 plus 1 by R2. See, 1 by R is actually Ka by L for the composite rod. Suppose the effective thermal conductivity is K and effective area is 2A and length is L. Okay, so for the composite rod it is K into 2A by L. For the first rod it is K1A by L and for the second it is K2A by L. Okay, now this A by L, this A by L and this A by L can be cancelled. Okay, so 2K will be K1 plus K2 or K will be K1 plus K2 by 2 or it is the arithmetic mean. Okay, when two rods are joined in parallel. Okay, now let's see what we have next. A spherical black body with radius 12 centimeter, radius 450 watts, power at 500 Kelvin. If the radius were halved and the temperature doubled, see the power sigma A T raised to 4 and sigma area of a spherical surface will be 4 pi r square then T raised to 4. So the power is proportional to r square and T raised to 4. So P dash over P will be r dash by r whole square then T dash by T whole raised to 4. R dash is given as r by 2 and T dash is given as 2T. Okay, so r dash by r will be 1 by 2 whole square then T dash by T will be 2 whole raised to 4. Okay, so this will be 2 square or we will get P dash equal to 4P. Okay, P is 450 watts. So 4 into 450 will be 1800 watts. Okay, two ends of a metal rod are maintained at temperature 100 and 110. The rate of heat flow in the rod is 4 joule per second. If the ends are maintained at temperature 200 degrees Celsius and 210, the rate of flow of heat will be dq by dt, rate of flow of heat, depends on the thermal conductivity, cross-sectional area, length and temperature difference. See, we have two cases. In the first case, temperature at two ends are 100 and 110 and the difference is 10 degrees Celsius. Okay, in the second case, same rod is used. So there is no change in conductivity, no difference in cross-sectional area and no difference in length also. Okay, these three factors, okay, remain unchanged. Okay. And what about the temperature difference? In the first case, it is 10 degrees Celsius. And in the second case also, the difference between the temperatures at the two ends are still 10. Okay, so the rate of flow of heat will be same as before. Okay, means 4 joule per second. Now let's see what we have next. Steam at 100 degrees Celsius is passed into 20 gram of water at 10 degrees Celsius. When water acquires a temperature of 80 degrees Celsius, means see, we have steam at 100 degrees Celsius. Okay, that is to be converted into 100 degree water initially. Then that 100 degree water is to be cooled to 80 degrees Celsius. Then some heat will be released. That heat must be used to increase the temperature of 20 gram of water from 10 degrees Celsius to 80 degrees Celsius. Okay, let's do. Suppose m gram of steam condenses. See, when 1 gram steam condenses, the heat released will be 540 calorie. When m gram steam condenses, the heat released will be m into 540. What is that 540? It is the latent heat of vaporization. Okay, so m gram steam condenses, so it releases m into 540 heat. Okay, then that m gram water at 100 degrees Celsius will be formed. Now that water at 100 degrees Celsius is to be cooled from 100 to 80. The heat released will be mc delta T. Mass is m, specific heat capacity of water is 1, and delta T means it cools from 100 to 80. Okay, so this is the heat released when the steam condenses. Okay, it will be converted to water at 100 degrees Celsius, and it is further cooled from 100 to 80 degrees Celsius. Then this much heat will be released. Okay, now this is the total heat released when the steam condenses and the water cools to 80 degrees Celsius. Now see, here we have 100 minus 80, that is 20 m plus 540 m, that will be 560 m. Okay, 560 m, and on the right side here we have 70 into 20. Okay, so m we will get 70 into 20 divided by 560, that is 2.5 gram. See, originally, initially there was 20 gram of water. Now 2.5 gram of steam condenses, so the total mass of water present will be 22.5. Okay, 22.5 gram. Right? A cylindrical metallic rod. In thermal contact with two reservoirs of heat at two ends conduct an amount of heat capital Q in time t. The metallic rod is melted and the metallic rod is formed into a rod of half the radius of the original rod. What is the amount of heat conducted by the new rod when placed in thermal contact with two reservoirs in time t? Okay, now see, we have Q, the rate of flow of heat, that is equal to thermal conductivity, then area, then temperature difference divided by length, okay, and time t. Okay, this is the heat conducted in time t, right? Now see, let's multiply both the numerator and denominator by pi r square area. So on the numerator we will get pi r square whole square, and in the denominator we will have pi r square L. Okay, this is area into length, that is volume. We have two cases. In both the cases, volume will remain the same. Okay, volume remains same. Okay, time remains same. Temperature difference remains same. Thermal conductivity remains same. Pi square remains same. So we can say this Q directly proportional to R raised to 4. R raised to 4. Okay. In the second case, radius is reduced to half. R dash equal to R by 2. Now, Q proportional to R raised to 4. So, Q dash by Q will be R dash by R whole raised to 4. R dash by R is 1 by 2. Whole raised to 4, it is 1 by 16. So, Q dash we will get Q by 16. Okay. So, this must be the correct option. Now, a black body at 227 degrees Celsius radiates heat at a rate of 7 calorie per centimeter square per second. And that 227 degrees Celsius is actually 227 plus 273, means it is 500 Kelvin. Okay, see 500 Kelvin, and this is 500 degrees Celsius more. Change in temperature in degrees Celsius and Kelvin are the same. So if this is 500 Kelvin and this is 500 degrees Celsius more, then it will be 500 Kelvin more. or this is 500 Kelvin and this is 1000 Kelvin. Okay, now Q proportional to T raised to 4. So Q dash over Q will be T dash over T whole raised to 4. So 1000 by 500 raised to 4. Okay, so this is 2 raised to 4 or it is 16. And Q is given as 7. So 16 into 7, that is 112. Okay, so this must be the correct option. Consider a compound slab consisting of two different materials having equal thickness and thermal conductivity is K and 2K. The equivalent thermal conductivity of the slab is. See, the two slabs are connected in series. Okay, so the effective thermal conductivity will be the harmonic mean. When they are connected in parallel, effective thermal conductivity will be arithmetic mean. Here in series, harmonic mean 2 K1 K2 by K1 plus K2. K1 and K2 are given as K and 2K. Okay, so if you put K1 equal to K and K2 equal to 2K, you will get 4 by 3K. So this must be the correct option. Right? If the temperature of the sun is doubled, okay, the rate of energy received on earth will be increased by a factor of say 16. Okay. An object kept in a large room having air temperature of 25 degrees Celsius takes 12 minutes to cool from 80 to 70. Average temperature will be 75, surrounding temperature 25, so the difference will be 50. Okay, and it cools from 80 to 70 means 10 degrees Celsius in time t. Okay, that is equal to K into difference, that is 50. Okay, and it cools from 70 to 60 in time say T dash. Okay, the average temperature of 70 and 60 will be 65. Okay, ambient temperature 25, 65 minus 25 will be 40. Okay, if you divide these two, T dash over T will be 5 by 4. So this T is given as 12, so it will be 15 minutes, right? This must be the correct option. Okay.